Today we're going to talk about quadrilaterals and inscribing them in circles. So if we start with a simple quadrilateral, like a square here, we can see that we can inscribe it in a circle by drawing the diagonals to find the center and drawing a circle whose circumference goes through all four vertices. Now we can do this for all sorts of quadrilaterals, rectangles for example, but also for other quadrilaterals. So here I just drew one that's inscribed in this circle, but not all quadrilaterals can be inscribed in a circle. And so what we're going to do today is explore the properties of a quadrilateral that allows it to be inscribed in a circle. To do that, we're going to use a property from previously where we learnt that the angle at the circumference, so this angle here, is going to be equal so long as it's being subtended by the same arc. We can see that by, if we just move that over there, we can move this around, and each time I move this, the computer's going to recalculate the angle, but it's always staying the same. If I move this point, or this point, the angle will change because I'm changing the arc. But so long as the arc stays the same, the angle will stay constant. So that's useful. We're going to use that to talk about the angles inside quadrilaterals. So if I add an extra point here, and I connect these together, we get a quadrilateral. I'm also going to add the other diagonal. Cool. Then what we can see is if we label this angle that we've calculated here, that we've measured, we call it, say, A, this will actually be equal to this angle here. And similarly, this angle, which I'm just going to call B, is going to equal this angle here. And so on and so forth. So let's label the other angles C and D. So this is because each of these pairs of angles is subtended by the same arc. Now, we also know that the angles inside a quadrilateral add up to 360 degrees. And here we can see that the internal angle is given by A plus B. And here it's A plus D, and so on. So if we add up all the internal angles, we get 2 lots of A, 2 lots of B, 2 lots of C, and 2 lots of D. So if we write that down, we would have 2A plus 2B plus 2C plus 2D is 360 degrees. If we divide both sides of that by 2, we get that A plus B plus C plus D equals 180. And we can check that that's right by measuring those angles. So if I just measure B here, and C here, and D here, then I can add them up. Here, A plus B plus C plus D, and you can see that the result, which is labeled epsilon here, is 180 degrees. So we got the right answer. Now what does that mean? Well, it actually means that A plus B and D plus C together is 180. So these angles are complementary. Now if they were both 90 degrees, then they would be a rectangle, and 90 plus 90 is 180, so it still works. So we've actually proven that all rectangles can be inscribed in circles, but we've proven something much more general, which is that actually any quadrilateral inscribed in a circle, the opposite angles are complementary. And there you have it.